As my topic today on the discussion is like on collaborative robots and robot simulation, how these two topics are useful in the industrial view. The agenda of the talk would be like introduction to KUKA, overview of industrial robots and its applications, collaborative robots and its application in the industry. Then finally, with the simulation, that is the offline tool, and I'll be giving you a short demo of the same, like how the simulation is carried out and what are the factors to be considered in the real-time scenario. As already informed, like I have done my master's in mechatronics engineering from VAT University, and I'm associated with KUKA from past 5+ years. Presently I take care of business development in the South region, and previously I had experience with application, project management, and troubleshooting and other things as a single point of contact for the customer. As I just go into the introduction about KUKA, these two gentlemen, Mr. Hans Keller and Mr. Jacob Nepik, were the founders of KUKA, and the company is also named on this gentleman's name as KUKA. Keller and Nepik, Augsburg. Augsburg is a city in Germany, basically like KUKA HQ. So that is like headquarters located in Augsburg, Germany. If I just go as a history of KUKA, KUKA started up in 1898. At the time, it was like just an accessory in welding and cutting and some lighting applications at that moment of time. Once the gradual growth in the automotive industry made KUKA also to invest more and more into friction welding machines and 6-axis robots. And we introduced our first 6-axis robot in 1973, that is known as Famulus. Over a period of last 45-47 years, we have like lot of different robots in different payload categories and different reach categories. So as I was explaining, like we have different payload category and different range of series. So this was my first 6-axis robot, that is known as Famulus. Post that, like we had a lot of changes in this 6-axis robot, and now the modern 6-axis robot would look something like this. And we have some dedicated robots for the entertainment purpose. Like this is one particular robot. And the present topic, that is nothing but like collaborative robot. This is one of the collaborative robot what we have it in our database. So actually, if you go see our robot portfolio product range, we have product range from 3 kg payload to up to 1.3 tons. So this is how how KUKA is working in the present market. Our major customers are from automotive industries, and then automotive tier ones and electronic industry or some machinery industries or any kind of another channels of industries. And Swisslog is one of our sister concern, which is located in US again. They take care of ASRS systems or like this unique commodities or such kind of projects will be taken care by this Swisslog team. And we have a dedicated healthcare team as well, which is again taken care by Swisslog. So if you see, where is KUKA available in the market? So we are available in automotive industry. We are available in aerospace, electronic, consumer goods. In the consumer goods and e-logistics and e-commerce, the main thing is like the ASRS systems. So in these ASRS systems, like you can see in India, Flipkart or Amazon or as such. So they all are our customers here in India, especially in e-commerce and logistics. Then we are into healthcare, and even we are into robotics, service robotics. So KUKA actually all across the world, we have 28 different subsidiaries. And KUKA India is one of the subsidiary. It is a 100% subsidiary of KUKA HG. So this one a small presentation or a slide, like where do we sit in the market. In the automotive industry, we are number 1, and with the general industry, we are in the top 5 in the worldwide. And again, if you see body and white, we are number 1 in US and number 2 in Europe. So these are some major applications that we can see it in an automotive industry. The major applications, like if you say in the automotive industry, like from the initial sheet metal. the sheet metal as a raw component till the end product, the complete painted product, to the like complete assembly, everything, the complete line is coming out. We have a complete robot setup in all the applications and different locations. So you take any name, any particular application, the robots are installed over there, and it is like you can see zero manpower used over there. It's only like the raw material to be loaded into the machine or like to the initial phase of the line. So other than this automotive industry, the other major industry that comes into picture is like the general industry, where like medical things come up, or plasma cutting, or like material like MIG welding or TIG welding or material handling application. And one such application is like for educational institutes, where like we do have like dedicated robots, like especially you can say those are like tabletop robots which are used for training the students and make them compatible like before they leave out the college and they are ready for the industry. So we have some dedicated educational cells for it. So in the present market, as like my co-speakers would have already spoke about this, about like industry 4.0 or like what are the new trends in the market. So industry 4.0 is one such area like where KUKA is also working intensely to make the line as a very more stable line and take the things ahead into the market. So this is how like in KUKA like offers like for this industry 4.0 like the data communication. We are into different types of communication, different kinds of APIs. Like we can access it from our mobile or a tab. Any data can be accessed, and the data transfer between machine to machine, each and every machine can be transferred. So, and if any mission is going to fail in prior, so we can give some inputs to the customer as well that this mission is going to fail. Just make sure that everything is ready so that the whatever is the downtime that is less. So as I was mentioning about like our training cells, this is how like one of our training cells look. So we have dedicated training sessions that happen in our KUKA Pune office and KUKA Gurgaon office. That is known as KUKA College. So we have presently like almost 4,000 plus industry personnel, students. They have got trained over here in our KUKA College. So if I say like these are two of our main offices that are located in India. One is in Gurugram in NCR, the other one is in Pune. So if you see the major customers in the market, like you take any of the OEMs or any of the tier ones in the market or tier twos in the market, we are always available over there. So these are like few of our major customers here in India. Okay, so this was all about like KUKA and what we do it in KUKA. Just a small brief idea about KUKA. Now we'll just jump into industrial robot. Before going into collaborative robots, first we need to have a small idea about the industrial robots. I think many of my co-speakers would have spoke about industrial robots and how it is being used in the market or in the industry. So I'll just give a small glimpse on it and I'll take it ahead. So what is an industrial robot? An industrial robot is an like reprogrammable machine, automatically controlled, and it can do multiple operations. For example, if I have a 6-axis robot over here, this robot is reprogrammable as per our request. So it can do MIG welding application, it can do TIG welding application, it can do material handling, it can do laser cutting, it can do laser welding, or you take any of the options. So this particular robot is reprogrammable, it is multi-purpose and programmable. And one more main important topic about this industrial robot is any axis less than 3 axis is not called as an industrial robot. As an industrial robot, we would require minimum 3 or more axes. So in this picture, as I could showcase over here, here I have an 6-axis industrial robot. So basically like here what it refers to KUKA Quantec. KUKA Quantec is one of the family of series of robots. We have different series, Quantec series, Nano series, Cybertech series or Fortech series as such different series based on the payload capacity. So this is one such kind of an 6-axis manipulator and standard industrial robot. And this industrial robot has to have a control or in control box. So this control box or the controller that is known as KRC4 controller. That is nothing but KUKA robot controller 4th generation. So this complete controller access like the all my 6 axes, and if I have any dedicated additional axis as a linear track or a positioner, and I'll just give you more inputs about this linear track and positioner, all those things when I just go into the simulation part of it. So all these things or the drive unit or everything has been used in this KRC4 controller. So, and now we have a control unit, we have a 6-axis robot. Now, how do I interact with all those things? So the third option is nothing but my smart pad. This smart pad is nothing but like where you program the robot, where you give the instructions to the robot, where you make all the different changes or what is a process to be followed by a robot. If I say in a layman language, the robot is completely just a small toy you can see. It's like a toy. It doesn't know anything. Whatever you teach to it, it does it. So this complete programming of this robot and what are the things to be done, everything has to be done using a smart pad, or like the robot jogging or the programming part, or if you need to put some kind of an interlocks within safety part or anything as such, everything can be accessed using our smart pad. The other last one is nothing but our softwares. As I was mentioning about simulation software, so we have like different softwares. One such software is like simulation software. Other than that, the simulation software, we have something known as like configuration softwares. So this configuration softwares is required for an industrial robot or a cobot or any kind of a robot. So what does this configuration software does? So it exactly replicates what is in the real-time world. Let me see, I have 4 robots. I need to configure it. I have 4 robots. Okay, I have 4 fixtures. I have 8 fixtures. Or I have like 2 control panels, like higher level controllers. All those things has to be controlled or like it has to be configured. Only then the robot knows, okay, I have 4 robots. I have this many softwares or this many things to do. So these things should be occupied in our control system, and those things can be configured using our softwares. Now, if I say, like, as I mentioned already, like as an industrial robot, it needs to have minimum 3 axes, and the maximum number of axes can be any number of axes can be added. So the first type of an industrial robot, you can see it's a Cartesian robot. So in a Cartesian robot, we usually have like X, Y, and Z coordinates. So it can just move in only X, Y, and Z directions. It cannot rotate or it cannot have any other directional movements. The next one is SCARA. SCARA is a 4-axis robot, and which is a very fast and very quick robot in the market. So this particular robot is used in the market, especially to handle like this biscuit packets or like the fast moving conveyors, like to handle different components. This kind of SCARAs are being used in the market. Then comes like the articulated robot. The articulated robot, as I already spoke, it is our 6-axis robot. And previously we saw a Quantex series robot. This is my Agilus series robot. A smaller robot, you can see bigger than SCARA, and a bit smaller than my Quantex series robot. Here I have payload of from 3 kg payload to I have 10 kg payload in this particular series. Then if we go to Delta robots, like Delta robots are nothing but like you can see the linear robots in the market. So again, this robot is also particularly used similar to an SCARA robot, but here this robot will be always put in the mounting in a ceiling condition. So these robots, we cannot put it on a floor or so. So these robots will be always put onto a ceiling, and it works in that way. The last one is nothing but my collaborative robot. So what makes this collaborative robot all different from all the other kinds of a robot, and what is the most specialty of this particular robot is it's like human collaborative. This particular robot can work intact with a human, so it can share the same workspace. So both human being and the robot can work in the same workspace. But when you say the other 4 robots, the Cartesian, SCARA, articulated, or Delta series of robots, these robots require some kind of an additional fencing or some kind of an safety part, or like Other things like different kinds of and safety regulations, and like it has to follow some ISO safety conditions. So dedicatedly, those are like in those cases. But when we need to have like one to one, like both human and robot in the same working area, we need to go with a collaborative robot. I'll just explain you more about this collaborative robot in our further slides. So here in this like a video, I like there is a short video about like now as we saw like different applications over there. Like I will just showcase a small short video where like different applications have been showcased. If you have any queries or anything, just please make a note of it. At the end of the session, we can have a short questionnaire on this different kinds of an applications or any other queries. So as we saw in our like previous applications, this was a short video of different applications that are like used in the market. Other than this, like we have a lot of other applications in an industrial view. So if you see like as just as an like an automotive industry, I could say there was a very small video. So in an automotive industry, there are like from press trending application. What is a press trending application? In a press trending application, the raw sheet metal is kept into the press, and it's not a single press. The press will be in a series of presses so that like the exact frame or the exact picture of this like complete sheet metal is got in a set of 5 to 6 presses in general. So this complete press is automated, and from this automated line, then when we go to this assembly of this sheet metal as a complete body or the automotive underbody, or so in this robot like underbody, like what is the role of a robot? There are like lot of welding applications that are involved over there, so that if we do a normal welding or like an skilled labor is used, again like it is a very tedious process, and it may not be like since we need to have like the number of cars or the number of automotive vehicles that needs to be delivered cannot be met. So from the scratch to the end, the robots are being used. So and the next once like this welding the underbody is ready of the car, then the outer frame or the sheet metal work. Here we are going to use a different kind of a welding application that is known as spot welding application. So in this spot welding application, the complete car body is welded, and like then the next part is like adding the different accessories in the car. Might be the engine, the bonnet, the seats, etc. Everything has been assembled. Once the assembly is done, the next part is like the painting part. Everything is done. Then it comes for a testing part. Now, the major role of a cobot over there is in the assembly area and in the testing area. So these are the two major areas in an industry, especially where like a cobot is really required, because in an assembly area there is like always a human intervention. Again, in the testing area, there is always a human intervention. So these two areas are like a main focus in an industry. Other than this, like where other things like where a cobot can work is in an automotive industry is like for a sealant application. Basically, what happens in a sealant application? There might be due to some changes in this structure or some changes in this whatever the glue is that is going over there. So the cobots are mainly used over there also for the gluing application. So what is the difference between a robot and a cobot? As I informed like or I explained some time back, the robot and a cobot that differs is like we have a common working area between a human and the robot that is only applicable in a cobot. When we say a robot, it cannot work, both human and the robot cannot work in the same shared workspace. And the cobot, it can work hand in hand. For example, like there needs to be a heavy tire that has to be like assembled to the car. Just they would put just the tire over there and the complete screwing application, or like if you say the engine part, there are some screws to be put over there. Those kind of an job, or like just to handle this, what do you see, the tire also to the like what do you say, like automotive part. These things can be worked along with the robot. So as you could see, just a definition of it, cobots are robots which are intended for direct human robot interaction with a shared space. So this is a very important point that differs from a robot and a cobot. So what makes a robot as a cobot? So what happens in a real-time scenario, like when the robots are there, like it is working in its full speed of 100% speed, and there might be some chances of any accident or due to some misusage or something, there is an accident. What happens, like we have something known as collision detection. This collision detection is available in both robot as well as the robot. But what happens in a robot? In a robot, like once a collision has happened, there is a huge, what do you say, the loss to the peripherals or to the human being over there. Because what happens, the collision detection in a robot, how it works is, it works on an voltage and current basis. So based on this feedback of voltage and current, the torque changes. So we have a dedicated torque. So the minimum and the maximum, the tolerances levels have been set in the robot. So based on that tolerances limit, the robot, like after having a like accident or having a hit into a particular machine or an human being, after it reaches its threshold limit, only then the robot stops. So what happens in a cobot? So in a cobot, again, we work on the same principle, taking the voltage and current feedback, but in an altogether different way. So what we do is like we use torque sensors. These torque sensors are put into each and every individual axis, so that like the torque is being like immediately checked, and the tolerance limits over here in a cobot is very low, so that even a small feather touch, to the cobot stops. So that there is no, like even though if there is a direct like interaction between a robot and a cobot, like a robot and a machine, so there is like if it is a cobot, there is no damage to the human being or there is no damage to the any of the peripheral items over there. I can show some of these examples in my next slides how it works in the industry, and where are few of the applications where the cobots are being used. So the main difference is this, and we have some limitations with the cobot as well. So what are those limitations? So in a cobot, what happens, like as we have it in a normal robot, the robot can have up to like 4 meters reach or 4.5 meters reach, all those kind of an reach is available. But in cobot, what happens, it is restricted to a smaller reach, and the payload of these cobots are limited as well. So we'll not have a cobot like having a payload capacity of 1 ton capacity as we have it in a robot, or we do not have a reach of like around 3 meters, 4 meters reach as we have it in a the normal robot. So those are like some of the small what do you see drawbacks of a cobot. So in the present industrial market, all OEMs are looking at this kind of a cobot, how to increase the payload of a cobot and how to increase the reach of a robot without like changing its basic specification as a collaborative stuff. So this is like a present trend that in the market, like, or in the future of the robotics, the cobots will be having like much more reach and much more payload. Then now in the present market, since we don't have a higher reach and higher payload capacity, we have something known as AGVs. What we do in an AGV. So, as you all know, like AGV is an automated guided vehicles. These automated guided vehicles have different kinds of navigation systems, radio waves, vision cameras, magnets, laser scanners, and different things. So, in the present market, these are the two major topics that are working upon. So, AGV, what happens in an AGV? So, this AGV is also made in such a way that it is also collaborative enough, but not a truly collaborative enough. But yeah, to an extent, this is also collaborative enough, so that if there is any intervention of any human being in between in the path of an AGV, so there is always this AGV stops. So in the present market, like what we are doing is like we are putting an AGV and a cobot working together. So what happens when we have this AGV and a cobot working together? We'll be having an higher reach. Might be, for example, I have an underbody of an automotive again. So this underbody of an automotive needs to be carried to different locations in the like operation one, operation two, or operation three as such. So if there is no interlink between different operations, we can use this kind of an AGVs and like AGVs along with a cobot to transfer the material from one location to other location as well. So there are lot of intense study that is going on this AGVs again. So as we were discussing about this, where are this our cobots that are being used in the real-time industry? So I'll be showing you some of the real-time scenarios, and this few of the videos or like this operations are from, the first one is from BMW. I'll just play this video. So as we saw in the video, when the cobot is doing an operation and when the human being is doing, an operator is doing an operation. So if you could see, the mating of the gears is much more easier in a cobot, because the cobot is not just only placing the component and the gear in the like area, it is also checking the exact fittingness of this. So this kind of an operation cannot be performed on a normal robot, because what happens in a normal robot, the robot just picks the material and it just places the material in some particular area, because it doesn't check, it doesn't have a feature to check the torque, or it doesn't have a feature to check like is the mating done properly. But in a cobot, what happens, the cobot can be programmed in such a way that it sets the gears, both the mating gears, in a such a way that the exact torque is met inside the cylinder. So this is one of the major operation within cobot. So as we saw it here, so it was like truly collaborative. So even a small touch or like a feel, a small jerk over there, the cobot stopped. Or this cobot programming can be made in such a way that like a small feather touch, even a small feather touch to the cobot stops. So here also we have a feature. What is the sensitivity level of this cobot? Might be what is like 5 Newton or 100 Newton force. What is a Newton force? What is a force that is to be required? So those kind of an fixturing or like this kind of an values to be given into the cobot, like as we do the cobot like calibration or the configuration. So I have one more example. So again, as we see in this particular, what do you say, like the operator was loading different kinds of components, and there were like lot of things that has to be carried out, which is should be in hand operations. In the last case, it was like the operator used to just keep an like just a panel over there, and she used to leave the area. But in this case, both the cobot and the operator should work in the same workspace, and you could also see that in between there is an impedance level that is set. When the cobot was in the entrance of the operation, the operator can easily move the cobot. So in a normal robot, this kind of an operation is not possible. We cannot move the robot like using a small force, using an like layman's hand, because there is a huge force that is required for an move the robot. But in case of an this kind of an cobot, the impedance level is very low, so that it can be easily moved, or it can be moved to a different location, and you can just start the cobot again. So it starts scanning the area again, and it starts working over there. So these were two of the examples at BMW plant in Europe, and like way over there, like there were like a lot of like human power, or like the like operator level has to like the operator has to perform lot of activities, and there is an human intervention always. Now I have a similar requirement, or like we had a similar requirement here in Kuka, India as well, for that is for Ford. So in Ford, what was like our main challenge was like there are like some nut runners. These nut runners to be placed on the engine without with the ease. If the ease like the normal, if you go with a normal robot, there are like chances of like this nut runner getting damaged, or this nuts getting damaged, or it is getting torqued with a higher value, or like it is not torqued into a perfect direction. So what we had is like we had a cobot option over there, and we used a nut runner so that all the nuts are put intact. And we had a very good cycle time as well, because customer had a very huge cycle time requirement. So we performed a huge cycle time like whatever was the customer requirement. This is one of the case study from Ford. If you could have observed over here, this nut runner was not directly going into the nut and it is not just doing a tightening application. So if you could see, the cobot is actually getting adjusted to the torque required and it is adjusting the nut as well. If you could closely observe it. So at the last, as we could see, there is something known as calibration as well. So what is the calibration over here? So we have, all, as I informed already, like at each and every joint, there is something known as joint sensor, like or the torque sensor that has been integrated in each and every joint. So this torque has to be also be adjusted. So we have set the values. Okay, this is my minimum area and this is my permissible and maximum like torques. So based on this torques, the robot or the cobot, you can see it automatically calculates its own torques. Is it in the well within the area or like well within the region? So this kind of an calibration is also done automatically, which is which cannot be performed in a normal robot. So at the end, you could have seen the cobot was just being handled by a very small force, might be just a small touch. So it is taking the force in that particular direction and it is moving in that direction. Once we stopped applying the force onto the cobot or onto the end effector, it started performing its own work, which was pre-programmed already. So this is how the mainly the collaborative robots work. So which cannot be implemented in a normal robot, or the normal robot cannot be just like we cannot just drag the robot or move the robot to a particular location or change its location. So this is one of the major other advantage. The impedance level of the cobot can be controlled. So these were like the main things, like some case studies about the cobots. And at the last, as I was mentioning this, along with the cobots, we have this AGVs. Those are in the future of the market or the future of the industry. So I have a small case study on this AGVs as well. So, as we saw in this particular simulation study and along with a real-time study, so this particular AGVs, how are these AGVs communicating each other? So this is working on something known as SLAM navigation. This SLAM navigation, what is the SLAM navigation? This SLAM navigation is nothing but like as we use our Google Maps. So in our Google Maps, we specify like we are at A location, we need to go to the B location. So in the same way, this AGVs are just given a direction from point A to point B. So this point B, it starts moving the complete area or the complete workspace of this complete installation or this complete office or this work area has been already predefined. So it start working in that direction. And for example, it starts moving in the B direction. And unfortunately, if you say there is an enclosure or there is some new item that has been put onto the side, so this AGV automatically calculates its path and it starts taking a deviation and it goes to a new location. And if you could have seen, the direction of this AGVs can be in a straight line, angular path, or in some particular curve, or it can also rotate in its own location as well. It can rotate completely. So in this particular AGVs, we have AGVs starting a range of 200 kg payload to up to like 25 tons. So these are like some of the things which are like the modern trends that are going in this AGVs. So in between the case study also you could have seen the AGVs are being used in the aerospace components, especially since these aerospace components are very huge enough to handle it. It is a very big challenge. So we have used our AGVs, especially in this Boeing, factory. So we have like there are completely all the AGVs working around for the material handling or for the ease of carrying the material. Okay, so till now we spoke about like cobots and a few small inputs on AGVs. So how a cobot and an AGV can work together in the market and it can revolutionize the next industries. The next part, this was like the first part of my presentation, and the second part of my presentation is nothing but like my offline tool or the simulation software. So what is an offline tool or a simulation software? So what we do in this offline tool? So in this offline tool, what we do is like we just replicate the exact real-time system. Or if you see like I have a robot, I have a fixture, I have an PLC, I have an different kinds of an what do you see gripper, I have an spot gun, I have an arc welding application, whatever it is. So whatever is a real-time replica, I just do a replica of the real-time scenario into this simulation. What is the use of doing this real-time whatever is the real-time scenario to just to make a replica of this in the simulation software? What is the use? So the first use here is the save. It saves the time. So for example, let me consider like I have a robot with 2 meter reach, and I don't do any simulation study, or I don't do perform any background calculation of it. On a rough calculation, we just go over there and install it. Unfortunately, it seems like might be the robot is not reaching one particular area. Might be the farthest area which requires 2.1 meter reach of the robot. Again, what we need to do is like either we need to get the both component and the robot nearer, or again there should be like they need to rechange the layout, or they need to reshuffle the layout so that the robot fits into that layout. So if they would have done this simulation study in the prior, so we know what is the location of a robot, what is the location of a PLC, what is the location of a component, or what is the location of a fixture. So each and every item can be fixed, or it can be put into the right direction. So this saves the time. So this is one example of an saving time. The other example of saving a time, for example, I need to do an arc welding application. So in this arc welding application, the angle of the torch is a very important key role. So if you don't maintain a correct welding angle torch, if you don't give a perfect push or pull angles, so we will not get an perfect weld, or the weld whatever we get, it would be with some porosity, or it would be like the weld penetration is not good, or like we'll get like lot of issues with the welding application. So these kind of a things can also be like put across into the inside this like simulation. And in the simulation study, we can do a complete study how it is done and how the calculations are done, and what is the angle, what is if there is a change in angle, or if there is a change in fixture, any modification required, we can do it in the first shot itself before going for a manufacturing of it. So it saves a lot of time over there. Then increase revenue. What does this increase revenue refer to? So as we save the time, the revenue has got increased. Other than this saving time, if there is any modification or a rework to be required in the real-time scenario, each and every rework makes lot of expenditure. This expenditure can be cut short to as minimum as possible. So in general, it is very easy to make a new fixture or a new component easily. But any kind of a rework on the same fixture, or any kind of a rework on the same component, takes a lot of amount. Or you can say not only the in the point of an cost factor, it also impacts like the labor part over there, and the rework is not always an again and not a perfect one. It's always a rework is a rework. So we can cut short all this rework, or like additional time spent, or like any kind of these things like which will increase the revenue. Also, what is the other case of an increasing the revenue? So for example, if I start explaining something like each and every time like to like some XYZ person, it's just only I'm giving an oral commitment. But the same thing, if you could show a small video of it, so this is how your system would look like. Might be this is your robot, this is your fixture, this is your PLC, and this is how it is going to run. So it makes the person whoever is having a look of it, it gives a very first glitch a very good glitch. So this again increases the revenue. And then the feasibility, as I already mentioned about the feasibility part, this is very important, like to check the complete feasibility of the system or the complete work area, everything is perfect or not. Without doing a feasibility study, we go to a real-time scenario and put the robots in a real-time scenario. There might be a lot of issues and lot of other criterias, and we need to change a lot of things. So this is about feasibility. Then planning reliability. What does this planning reliability refer to? So if we have a clear-cut picture of what we are going to do, if we give the same planning to the person who is going to execute in the real-time scenario in the industry, he has a very clear-cut idea, and you can do the planning or like all the required accessories like in a quick way. So this is a way and the simulation works. Then the other thing is the modular. What is this modular and offline tool? So in the modular, so as I was explaining few slides before, the robot is just a bare robot. It doesn't know anything. So if you say like to do arc welding application and give the commands to the arc welding command, it runs an arc welding application. If you say pick and place application, it runs a pick and place application. So in this modular commands, so we can put different kinds of a module in a simulation. For an welding application, we can put an welding module. For an like pick and place application, we can just put an pick and place module over there. So this complete modules, what are the required modules required? We can just select the required modules before going to the real-time scenario as well. And what happens like by doing all these things like increasing revenue, feasibility, planning, modular, all those things. Other than this, we have one more major advantage of doing a simulation or an offline tool. So in this offline tool, what we do is we would have already replicated the real-time scenario in an like software, and the complete programming of the robot can be just done sitting in an office. And whatever is this program that is being generated, once the robot is on or like my complete system is on, I can just transfer the program sitting in my office, and I can send my program to the real-time controller and real-time PLC, and those program can be run over there. So no need to have a like dedicated person who goes over there. He stands like and he works on this robot and he programs the robot, and which is a very tedious process and a very pretty long time process. So we do this simulation and we just generate the program, and the same program is transferred to the real-time controller, which is a very quick way and a very feasible way of doing an offline simulation. So if you see this robot simulation software packages, in the present market, there are a lot of simulation offline software tools. I've just listed a few of major companies who are doing this offline robot simulation softwares. One is from Delmia, again that is from Dassault System. Fusion 360 is from Autodesk. Actually, Fusion 360 is a combination of there are few of their couple of combinations like Power Mill and few of their additional combinations. They have made this Fusion 360. And Process Simulate is by Siemens. Process Simulate is nothing but like it is an upgraded version of RobCAD. RobCAD was the previous name, and now they are using this Process Simulate as an upgraded version from Siemens. And we have KUKA Sim, a dedicated software from KUKA end. So we have like our own dedicated software for the simulation purpose that is known as KUKA Sim. And we have MasterCam. So again, this MasterCam is also one of the major simulation softwares that are being used in the market. So all the above were like the paid softwares, and might be if you need to carry out like some kind of an freeware, we need to just have a check of a simulation for just for that. In that case, we can go with RoboDK. RoboDK is a freeware, but there are some limitations with this RoboDK. So presently, I would like to give some more inputs about like this KUKA Sim, or like I'll just give you a small live demo of how a simulation is done from the scratch, and I'll just showcase you like few of the other things what like in a simulation that can be done, and how the processing is done and how the data is taken. As I was mentioning, like we can directly take the data from the simulation and directly that can be put onto the real-time controller. How those things are done, I'll just give you a small live demo of that. Before going to the live demo, I'll just like to give a small overview or a briefing of this simulation software. In this simulation software, basically we have like 4 different tabs. One is my home tab, the second one is my modeling tab, the third one is my programming tab, and the fourth one is my drawing tab. So what are the different tabs, or what are the different uses of different tabs over here? In the home tab, so in the home tab is a home tab, like if you can say like it's the area where we are going to build our complete layout, or my complete simulation is built over there. So if I need to have an PLC, or I need to have a fixture, I need to have a robot, I need to have a conveyor, or I need to have a welding application like spot gun or like welding torch, or I need to have a gripper or any kind of a things. So all these kinds of things, everything is readily available in my home tab, and I'll do everything is required in that home tab. Then something is known as modeling. There are some things like which is not available in my home tab, or like which is not available in the default system. We can directly do a modeling here. So using this modeling, we can do some kind of a modeling here, and those models can be again used in the program. Now the next part is my programming tab. What is this programming tab all about? In this programming tab, so it is all about like how the program is done, how the logics are wrote, how different commands are wrote in the robot, and what are the interlocks, what are the safety interlocks, what is the working area, what is the non-working area. All those things can be defined in this programming tab. Once programming tab is done, I need to just export this data to my real-time scenario. So I can do it in two different ways. I can just create a 2D drawing of the complete layout, what I have done. So that comes in my drawing tab. And if I need to just select like some offline programs, so the offline program also can be again taken from my drawing tab and my programming tab. These are like two different major areas to export the data from my offline tool to real-time scenario. Now we'll just go for a small live demo. So as I was explaining about like KUKA software or the KUKA simulation tool, so this is my simulation tool. So if you take any of the other simulation tools over there, what I have mentioned like Delmia or Process Simulate or AutoCAD, like PowerMill. So all the simulation software would like replicate the same, almost it would remain the same, but there would be some changes in the namings or like some changes in the programming tabs, or like the way of the process might be slightly different, or all across it would remain the same. So I have a standard library over here. In this standard library, I can just browse different like robots, like I have KUKA robots here. I have like different payload categories. As I was referring to, like we have like payload category from 3 kgs to 1.3 tons. I can select whatever is the robot type which I require. I'll just select one of the robot type from my subattack series. So one way is just double click it. So my robot is into the workspace area, or we can just drag and drop something. Let me say I need to handle, I'll just showcase a small example of how an handling application that is being done. So I'll just say I need to handle this block. So I'll just select these blocks. And as I was mentioning, like we can do all the necessary changes to this block or whatever is of properties, we can do this like this. And we can, as the feasibility study, I need to know what is my incoming area, what is my outgoing area, and what are the other things. For example, let me see, this box is just coming on a conveyor. So I need to replicate in the real-time scenario, a conveyor is also to be used over here. Let me see a conveyor. So I have a conveyor here. So just to generate the components on the conveyor, I need to have some of the basic changes that has to be done, and I'll be just replacing this area. Okay, why I'm doing this area? Because if I just say my picking area for this robot, there is a like this comes with 1.6 meters reach. Okay, this as a particular reach area, I cannot go after that. So I'll just show you a 3D area. So this is my 3D area, or this is my work envelope. So this is my work envelope. If I have a component in my work envelope, I can just go, I can pick it up. So if I don't have a component in my work envelope, I cannot do anything. So I need to put all my peripheral items. So in my working envelope, let me see, this has to be coming into my working envelope like this somewhere. So in the same way, like I need to put across all the different components into the layout, so that like every component is available in my working area. This is one kind of an working area what we are going to put. And the other things over here is, so if you could see, there are like lot of items that are like the lot of cables that are coming onto the robot. So these are known as like some additional peripheral items which are not required actually in the real-time scenario. So this is a mount plate which is used for mounting the robot. This is an energy supply, if you could see. So this energy supply, it differs. What is this energy supply? For an pick and place application, I need to have some kind of an, what do you see, to create a vacuum, I need to put some cabling, or I need to put some kind of a sensor. So I need to have this kind of an energy supply. If I say I don't require any kind of an energy supply, so I can just work with my bare robot, so we can just remove it. The other one is the lift tools. So this lift tools is nothing but like to just to carry the robot from one location to other location. This lift tools are used. Now what I'll do is like I'll just do a small configuration of it. So this particular component is going to generate the components. For example, my default component, if you could see over here, I'm just running it. This is just default component that is running onto this, but I don't require this. I need to have this kind of a small component over there. So I'll just go to modeling tab and I'll just save this. As I was referring before, anything that is out of this thing is like we need to save it. So then I go to again to my programming tab. Then I just give the path of this block. So this is how like the simulation that got changed. So this is one way. Now, just like what are the other components like that are to be added in this simulation? Might be I can get some inputs from all the participants over here. What are the other things in a real-time scenario that are required on a glance? Raju sir, am I audible?
Yes, sir, you're audible.
Yeah. If you like for all the participants, a small question. So, what are the other things you like? You say like for a pick and place application is required.
I'm just unmuting. The participants can unmute themselves and they can interact with the speaker. Sir, Vinod sir?
Yes, sir.
Actually, they were actually kept on mute. I think we can just proceed. At the end of the session, they'll ask the queries if at all they have.
Okay, sir. No issues. Yeah. For example, for this, I need to have a small, what do you say, gripper. I'll just rechange the gripper values. So, so now like let me say like my parts are flowing on my conveyor and all those things are done. So what happens in a real-time scenario? The robot doesn't know is the component available on a conveyor or not. So we need to have some kind of a sensors and some kind of an signal or signal handshaking between a robot and a conveyor. Only then the robot knows, okay, the part is available so that the robot can go and pick the component. So what I'll do is like, I'll just add some kind of a signals. So this is my signals, like these are like robot signals. Like I need to have an input that the part is ready or the batch is ready. So I say this comes on my 100 number signal. So in the robot, we can configure n number of IOs or like n number of digital signals from the robot to the real-time scenario or from the real-time scenario to the robot. So this is how it is being done. I'll just stop the signals. Then I'll just give a small TCP, that is nothing but tool center point. Presently my tool center point is here, but my picking area is here. So I need to just change it. So I just change my tool center point. So what is my tool center point? This tool center point is nothing but this is the area of picking location. Now I'll go to my programming tab. I'm in my programming tab. I'll just go to my job map. So now what I have done, like we have given a signal that the robot should wait for signal number 100, or that is nothing but my component ready. So my component ready, that is coming on my signal number 100. So this is how the same would be replicated in the real-time scenario. What they do is they just put different kinds of a wait signal or different kinds of an output signal. Just an output signal is used for picking up the component. Let me say my wait for 100 to be true. So 100 to be true, what does this 100 to be true refer to? So once a component is available for the picking area, so my 100 number of input will be high. Now I'll just jog the robot. So my jogging of the robot can be in two ways. So this is my axis number 1, axis number 2, individual axis movements, third axis. This is my fourth axis, this rotation. Basically my 4, 5 and 6 will give my wrist axis movements. As we have an wrist axis movement, this my 4, 5, 6 gives my wrist axis movement. The other way around. Each and every time if I start moving my axis, individual axis, it takes a pretty long time. So what we do, we need to move the robot in X, Y, Z directions. Let me say like this, X, Y, Z and ABC. Here you could see what is the direction and what is the angle. So in this way we can do it. And let me say this is my home position of my robot. Now, after the component is ready over here, the robot should go ahead and it should start picking the component. So I'll just write a small program. Let me see like how it runs. The component started flowing on a conveyor. So you could see once the component came, it reached to the area of picking area, the robot started moving. So this is way how the programming of a robot is being done. So let me say I'll do a small program here for just to pick and place of this component. Let me see, this is my picking area. So these are like some commands, like these commands can be linear command, these commands can be point to point motion, these commands can be some kind of a circular path. Now my robot is here. Now my robot is here. It has to grasp this component. To grasp this component, I need to give an output to the robot or saying that the gripper should open its vacuum and it should grasp. So I'm just giving this output 1 to be true so that it picks it up. Now, once the component is picked, let me see, I need to just go to this particular area and drop it. I'll say this is my dropping area. Now the component has been grasped. It has to be released. So the releasing is like I need to make this the same input which was like the output was high. Now I'll make it false, that is low. And I need to come back to the same position. So this is a small short program what we did now. Let me see how the simulation software works. So this was a small program just to have a pick and place application. I'll just run the program again. So the component is coming. So it is waiting. The robot is waiting for a signal that the component is ready. Now the component is ready. It just picks, it goes over there, it places it and it comes back. So this is one kind of a program. as we were checking about like the feasibility, this is one kind of a feasibility study. And now, for example, now the component has to be loaded inside a machine. I don't have this kind of a conveyor and this is an open area. So there should be something known as collision detection so that it doesn't hit anything in the workspace. So for that, we need to activate this collision detection. Before activating this collision detection, there is something known as create detector. Now, this is my group way. So my robot and my gripper is one group, and this group, if it hits anything, this conveyor, if it is hitting this conveyor, it should give an alarm. So then I'll go to B. I'll select this conveyor as my group B. Then I'll say close. Then I'll activate my collision detector. Now, if you could see here, so whenever there is a collision, there is a color change. So in this way, now let me do a small program. So I have made a program such that the robot is going and hitting this conveyor. So I'll just run this program. If you could see what happens. So it went and hit it. So it is just detecting that there is a collision, but the robot didn't stop. So to activate that, stop on collision. If there is a collision, the robot should stop. So yeah, if you could see, it had a collision with this robot, with this conveyor, and the robot stopped. So in the same way, if we have, this is a very simple example, if we have lot of other things in a particular area or like a complete line, there will be a lot of other robots working in the same area, same zone. Might be like 10 robots are working in the same zone. If one-to-one robot starts colliding, there is a huge damage to the robot. So we need to check this kind of an collision detection, and we need to propose a layout in a perfect way, and a complete program has to be built. So that is how an complete simulation software works. So in the same way, I'll just give you some more examples or like some live examples which we have done it. So basically this is one of an component. This is again for an like two-wheeler component. Okay, this two-wheeler component has to be spot welded. So in this case, we have used spot welding gun. So you could see, just see like how an software tool and how these things are working over here. So if you see, this is my fixture. So this is my fixture and this is my component and my robot and my robot controller and a PLC. Everything is put intact, and this is how the locations in the real-time scenario. I'll just play this. So this is how, like, you could see, like there are like multiple spots that are being happening, and if you could see, so after this many spots, it is pre-programmed with the robot and the PLC controller. After this many spots, this fixture, particular fixture, has to go back. So once it has gone back, the robot performs further activities. So this is one way, and the second way. So in this way, like we need to also check like if there is any falling with this particular area, or like particularly to this fixture itself, to the fixture itself. So all this kind of a feasibility study is done using a simulation software. So the robot goes to the home position. Once the new component is loaded again, the operator just presses like to go ahead, and the robot starts performing its activities. This is one way. And now let me say arc welding application. As I was explaining about different angles to be maintained. So here, this is not only the robot. There are two things in this. So as till now we were discussing only about the robots. Here we have a positioner. What is a positioner? A positioner is an external axis that is required for this component to move in different angles. Might be like this. So it needs to move in this direction, or it needs to rotate like this. So this kind of an external axis or known as positionals, linear tracks or spot guns, this kind of an external axis. And in this particular case, this complete fins to be welded automatically. There should not be any human intervention, because what happens, like the complete area cannot be welded at the same time. So there should be some different angles. So this is a small program that is being done for a TIG welding application. So this is a seam, it is being welded. So if you could see, like now, if the component was in the same direction, this area couldn't be accessed. So we need to have this tilt. And now we have this welding of this particular area. So if the component was just straight enough, we cannot perform this activity. Hence we use this positioner. As a simulation engineer or as the guy who is doing a simulation, he needs to take care of all those things. If you could see, there is a particular angle of welding. So all those things can be maintained and checked in the simulation. Without, if we don't have this simulation software tool or something, we cannot do this like each and every time in a real-time scenario and check each and every time is it perfect or not. So these are some live demos or like some live examples of simulation software or some kind of a case studies. So this is from my end. If you have any queries, we can go ahead.
Thank you so much for your presentation, sir. It's
Thank
really
you,
gives
sir.
a sense to collaboration robots and robot simulation. We can able to visualize that industry scenario of collaboration robot and their contributions. Thank you so much for your presentation, sir. Now the session
Thank you,
is
sir.
open for queries. Participant can ask their queries to respected speaker.
Hello.
Speaker, participant, it's kindly request from our side. Participant, please open your webcams. Yeah.
So I have a question, sir.
Sure, sir.
Say, I have no, this is all simulation. Do you have any real-time working videos, something like?
Real-time working, sir, as like?
Yeah. Yeah.
So real-time working in the sense like as I showed like some of the videos over there, like especially for the cobots, which
Yes.
was worked in BMW and in the Ford.
And one question. Why you are not using any vision sensors for positioning or checking whether the accuracy is there or not while you are performing?
Okay, so in this way, like the vision sensors, like even we have vision sensors which work in the different locations. But for this particular location, the robot what we have used already has a 40 micron accuracy. So 40 micron of positional accuracy, we already have it. So we don't require an additional vision sensor. Might be we would require some kind of an additional vision sensor in a case where we have a carton box that is coming onto the what do you say, conveyor, and in between we don't know the which phase is it in the right direction or not. In that case, we can go for a vision sensor. Or if you say like I have a bin of components, so the components are put inside a bin. I don't know the direction. What is the direction to go and pick it? So in that case, I may need to go for a vision system where I can have a 2D vision as well as a 3D vision. So using which I'll get the exact coordinates for the pick for a component. So it is based on the necessity.
Okay. So means we can have vision system install in this robot as and what are the connectivity like? Is it connecting with the NI lab use or?
Yeah, so the robots, like as I was explaining about Industry 4.0, that was what I wanted to explain. The data from the robot can be transferred to any external peripheral item, and an external peripheral item can send me any kind of a data. So that might be NI, or that can be lab view, or that can be like some like MATLAB. In MATLAB, I think you have Sinu something. I don't know. I don't know the exact terms. There is one particular tool in this MATLAB as well, where like the real-time data is being transferred.
So it is IoT enabled, right?
Yeah, IoT enabled some particular tool in MATLAB. Because
Okay.
MATLAB, if you say MATLAB, MATLAB is a very huge structure.
Yes, yes. Yes. Thank you, sir.
Thank you, sir.
Good afternoon, sir.
Yeah, good afternoon, sir.
I am Anil Kumar. I have one doubt, sir.
Sure.
Sir, in this simulation tool, you are explaining the working with the robots. Is there any possible to incorporate human models also?
No, we don't have that option. Like, or that is not required in the real-time scenario, actually, to see. Because what happens?
Actually, sir, now in collaborative scenario, we want to work the human with the robot with the power force limiting or manual guidance application, sir. For that
Okay.
purpose, we want to collaborate the human with the robot. If I want to do the simulation, we want to work collaboratively human with the robot. That's why in CATIA, the option is there, sir, for incorporating the human model. Is
Okay.
there any possibility to tell me or any COCA simulation?
So actually, like when we say like simulation software for robot, we don't have this option. But as you mentioned about like for this collaborative robot, we need to fix different values or different force that is coming onto the robot. This can be manipulated using like there are some additional softwares in the cobot. So when we go with the cobot in the real-time controller, there are some additional softwares where you can fix the sensitivity, or you can just change the torque sensors of each and every axis, the minimum and the maximum tolerance limits. So whatever is the testing you require, we can do it over there. Because I completely get you. Like in CATIA, I think there is something known as like you can apply this many of force, might be 10 Newton force or 20 Newton force or something as such.
Yes, sir.
Yeah, that kind of things are not available not only in KUKASM or you can say in Delmia or other things. They don't have it because CATIA is altogether a design software. And simulation software is altogether just we are going to simulate it. We are not going to design anything over there.
Yes, sir. Thank you, sir.
Thank you.